Welcome back, everyone. I hope you've got all your bits and pieces together. You've got a piece of paper and you've got a pen and you're taking notes and you're reminding yourself of all these important factors as we're revising chemical change. Let's have a look what we've done so far. We have dealt with the terminology and the concepts that are involved in energy and change. We're moving on now to rate and extent of reactions. These are very closely linked together, and some of the terms are going to be overlapping. But let's go and see exactly where we're at. We know what reactants are. Those are the things that you start with. We've seen that on the energy profile. We know what products are. Those are the things that you end with. Here's an important word, the word yield. Now, it doesn't often come up, but it's important to recognize it's different to rate. Yield is about the amount of product. We can even do calculations about the percentage yield. We're not going to do those today. But I want to differentiate between yield and rate. Rate and yield are not the same. Yield is the amount of product. Rate is the time it takes to make the product, or the time for the reactants to be all used up. So there's a slightly different distinction between rate and extent. The extent in the title of this section is about the yield. The rate is about how quickly or slowly we can get the process done. So rate of reaction or reaction rate is clearly defined. And so we define it as follows. It's the change in concentration of reactants or products per unit time. Now, it doesn't only have to be concentration. It could be the change in mass or the change in volume of either reactant or product. But the most common way to define it is in terms of concentration. And in fact, there's a formula for that. And I want to just write the formula down quickly and say to you, rate is going to be the change in concentration over the change in time. And so remember that this change in concentration over change in time is going to be the gradient of a graph. And we're going to look at one that comes out towards the end of this lesson, or the segment at least. So bear that in mind as we go on. Now, reaction rate is linked to collision theory. Remember, we've spoken about collision theory. It's that theory in terms of the molecules or the particles of a reactant moving around, bouncing into each other, colliding. Now, very important is the conditions and the requirements for that collision to be successful. Those molecules need to have enough energy. Usually, that's kinetic energy. As they come closer together, that kinetic energy is converted into potential energy. But they can't have too much kinetic energy because then they'll bump into each other and they'll collide off. We don't want that to happen. So they have to have not too little energy because the electron clouds would repel each other if they had too little kinetic energy. They mustn't have too much because then the nuclei of the atoms would repel each other. They've got to have just the right amount. It's called the Goldilocks factor. Just enough energy for them to overlap. On top of that, they've also got to have the correct orientation. What do I mean by that? It means that if we have a p orbital that's going to overlap with another p orbital, then these two p orbitals are going to have to be in the same direction. There can't be the one p orbital sitting here and the other one like that. Now, on top of that, those p orbitals have to have one unpaired electron. And it's only then that we can get a successful covalent bond. So please remember, enough energy, correct orientation, and that orientation means that the orbitals have to overlap in the correct way. And they have to overlap with the unpaired electrons in those half-filled orbitals. Very important. Now, the factors that we are going to look at are recognizing that we can increase the rate of reactions when the number of effective collisions increase. And the effective collisions are going to increase when we have the right amount of energy, and correct orientation. Now, what can determine then to get these effective collisions? Well, there's some things that you're going to need to list, and you must learn these factors. So let's look at the factors, and we'll show how they work together. The factors include the nature of reacting substances. So, for example, group 1 metals are highly reactive, where something like lead is hardly reactive, or gold, it's unreactive. So depending on the reactivity of the metal, or the non-metal, which depends really on the electron configuration, we recognize that different things can react quickly or slowly. So the type of material that you've got affects the rate of reaction. The surface area affects the reaction. The concentration also affects the rate of reaction. And when we talk about concentration, the equivalent of concentration for gases is pressure. Temperature is also going to affect the rate of reaction because temperature is related to the average kinetic energy of all the molecules together. So if you increase the temperature, you're increasing the average kinetic energy of the molecules. And we've already said, if those molecules are moving faster, they've got more chance to collide. And if that's the case, we're going to see an outcome of that. The presence of a catalyst. Well, the catalyst is there to lower the required energy to make the activated complex. It decreases the activation energy, and it usually does this by holding some of the reactant molecules in place so that passing them by, other things can latch on. So it creates a platform for this reaction to take place, which is slightly like bees around the honey pot, if you like. They're all attracted to this thing that's holding them there. If we've got gases floating around in the air, it's not likely that they're going to bump into each other. It's a bit like finding a camel in the desert. It could be anywhere in the desert, all over the place. Big area, not likely to collide. But when you've concentrated them around the oasis, then you'll find a camel that's there. And that's exactly what the catalyst does. It brings things together so that they can latch on and collide with each other. So let's look at the effect in terms of collision theory. So I want you to remember that surface area means that if you want to increase the surface area, you've got to make the particles smaller. Because there's gaps between those little particles. The more surface is uncovered. If you've got a slab or a plate, then you can't get in between them. If you crunch them down into fine powder, each of those little particles have a bigger surface area. So the bigger the surface area, the higher the rate. Small particles, greater surface area, increase rate. Now, the next one, concentration, which is pressure. If things are more concentrated under higher pressure, they're closer together, more likely to have effective collisions, increase rate. So if this is high, then you're going to have a high rate, big rate. Okay, if we talk about temperature, well, we've said it already. Higher temperature, more kinetic energy. So remember, it's directly related to average kinetic energy of the particles. That means that if you go increase this, then the rate will increase. And the presence of the catalyst we've dealt with. I've just mentioned that to you, so you've got that very clearly. Now, here's a typical question, and I just want to deal with two little aspects of this question. I've extracted just the data from an exam question, and I want you to do that yourself. Don't only look at the questions, look at the things like graphs and so on. So look here. The gradient of that graph compared to the gradient of that graph. Which one is the bigger rate? Well, you can see this one is steeper. So this one is high rate. Notice they finish at the same amount. This one finishes before that one. So what conditions do you think that are going to be in effect to make the rate higher? So to get graph A, I think it would be at a higher temperature. And what else? It might be at a higher pressure. Well, it's not, because that's liquid, so it's not high pressure. But what you could also think about, it's not more of, there could be a catalyst. Okay, so if you look at the reaction, this is peroxide making water and oxygen, and this was the collection of oxygen. So we've got the ideas very clearly seen. So use these to apply your knowledge and recognize that we can manage answering any question on rate of reaction. Now, just be clear about this. Recognize the graph could be different. If they asked you what would happen if the temperature was colder, well, you'd need to draw a graph with a lower gradient. And it might only go up to there. Right, we've done quite a lot of exploration of chemical change, but there's more to come. So take a quick break, and we'll be back straight after the break.